Thank you. Good afternoon. I'm Vinay Patwardhan from Cadence, Product Management Director for Digital Implementation and 3D IC Products. Cadence has been working on packaging and advanced packaging for the almost last 25 years. We are an EDA company that does EDA software, and talking about 3D IC now. Let me first start with what we have today and what we are working on for these next generation 3D IC designs. Okay, so starting with what we have today for today's 3D IC designs, we have heard a lot of things that are coming in the future, but there are customers doing 3D IC designs today, and we have integrated platforms for 3D IC design. I'll talk a little bit about it in the coming slides. But one key aspect that we've added is 3D partitioning and physical design flows for 3D place and route. I'm going to talk more about the physical aspects of the 3D IC design phase. We also have system level early exploration and multi-physics analysis flows that help model the system early on, and some of that information can be used to design 3D ICs in a more effective way. We have early test chip collaborations and reference flows with all major foundries. And we do have die-to-die communication IPs and other multi-die IPs that are a key part of the ecosystem. And we do offer services also to build some of these the 3D ICs or complex chips. If this is the first time you are going into the world of 3D IC or multi-chiplet design, we do offer some services for that. Now, let's look at, when we are trying to look at the complexity, I chose this particular picture because it does show that in a 3D IC, you're building multiple layers. And at each of these layers, there are different types of interconnects. And the scale of those interconnects is quite different. So for example, the solder balls that go on the bottom of the package are 1,000 microns pitch apart, but whereas the hybrid bonds that go on the top of the, that connect two dies, two advanced node dies together, are in the range of under 10 microns. So from an EDA point of view, when we are designing algorithms or our tools, we need to model and implement these connections with very high accuracy, high precision. We have to not only model the physical size, shape of that, we have to make sure that the electrical properties are modeled correctly, particularly of these die interconnects. And then the electrothermal and mechanical effects that some of the speakers talked about earlier have to be taken into account much earlier in the flow, so that the structural integrity of the full 3D heterogeneous system is pretty intact. So now, looking at the most challenging part, or what's new, is these hybrid bonds that are of very high, very small pitch. And for that, we need a system that will look at all of these together. So when you look at that part, when you're splitting a die, you can. I've divided this into stacking versus analysis as two separate challenges. In terms of stacking, you can imagine one advanced node die has so much data. So for multiple of these dies, managing all that data in an efficient manner is one of the key things that we have to look at first. Once we have a handle on the data management part, we can have chiplets on different nodes. We can differentiate between different nodes and do concurrent editing of multiple devices at the same time. So then things like on-the-fly splitting and repartitioning is possible. Currently, we do hierarchical design or partitioning in the 2 dimensions. Now there's a whole Z dimension added, so we have to develop some a 3-dimensional placement capability which can take into account the Z direction for extra optimization. And then timing across these multiple chiplets. Timing for digital dies is one of the most important checks. if you have synchronous clocks going across dies, how do you time them? Because if there are multiple technology nodes, and if any of you have worked on the advanced node designs, the number of corners that you have to sign off on is huge. So with multiple dies signing off on those many corners becomes a really big challenge. And then your bottom die still sits on an interposer or on a package. So there are some areas on the lower die that you need to reserve for those through silicon vias or other 3D structures, for which you have to be aware of those keep out regions for placing your standard cells. So some of these aspects are new for doing 3D placement, 3D design, which were not present in the 2D monolithic dies. So we have to take into account, if we are writing any kind of placers or placement checks, all of these have to be taken into account as an objective. Now, in terms of the 3D analysis and sign-off, I already mentioned about the STA. That needs some kind of an automated smart corner reduction for multiple corners. System LVS check is the most important when you're doing a design. We cannot wait for all the dies to be complete to do an LVS check. So early connectivity checking is a key part that we have to develop. Then there is, of course, EMIR, and that leads to power and thermal are closely related. So the previous speaker talked about the thermal challenges. It is a make or break check that we have to bring in early on into the design. And there was discussion about the 3D test standards. So I'll skip that part. So the good news is we do have a way today to take a 2D die and fold it into a 3D die. We have an automated algorithm to do that. It's based on the fine-grain auto-partitioning. It's based on our multi-objective 3D placer. And we have run it across designs. If you can, on the right side, I have a table which shows it's been run on a wearable design, CPU, mobile core. In each case, we do see area savings, we do see wire length savings. So whatever in theory that it's seen as a benefit of 3D, we have verified results which show that we do see this power performance area gain when you use this flow. And this is using real PDKs, homogeneous and heterogeneous flows. So taking this to the next stage is the big challenge now. Because when we started off with a basic memory on logic flow. We just take a big design, separate out all the memories, put them on a top die, put the logic on the bottom die. Customers wanted to be selective. They wanted some memories on the bottom die, so we enabled a flow like that. The middle flow, the user-specified die ID, is the most popular one with our customers currently, because most of our customers are saying, we know exactly what goes on the top die, we know exactly what we want on the bottom die. So we give them a guided flow where they can specify the location of a module where it should go on top and bottom. But going forward, as the size of the design gets big and as the complexity of nodes increases, we are marching towards a full logic on logic instance level granularity type of automated algorithm that needs to be developed. We have some ideas on how to do that for 2 tiers. We are working on ideas how to do that on more than 2 tiers. So any kind of enablement we can get, it needs some more industry research, needs some more university research, but we have a plan to get there, and we have a baseline platform to get there today. So just wrapping up my talk, as I said, we started off, when you're building a structure, we have to have a big basic foundation, a strong foundation. That is our unified platform with system level analysis. It's needed for, it enables early analysis earlier in the flow to build robust 3D structures in a HI configuration. Fine-grained die partitioning automation is available today, and we see that as the future that will enable some of these complex HI structures. We have identified some bottleneck reduction technologies, and we are solving them through co-optimization with package and dies all in the same database. And of course, this type of application with so many different parameters is an ideal one for using AI and ML. But that's a topic for another day. So through a structured implementation and a plan, I think we can get there to bring in this 3D IC schedule. We can pull that in, which seems to be right now a big worry that most of our customers have as to how long will this take. But we do have a plan for that, and hopefully with DARPA's help and all the industry partners and research help from the universities, we'll get there much sooner than what we plan. Thank you.